Good morning, everybody. My name is Brian from Chifeng from the Hong Kong University of Science and Technology. My team includes Mu Jiandong and Professor Jiang Wei. And today I would like to introduce a cost-effective CNN accelerator design with configurable PU on Fpga. First, let's look at the outline. First, I would like to introduce the background of the CNN, and of course, afterward I will discuss about the CNN design challenges and our proposed tiling method with approximate computing as well, and afterward the experimental results, and last we will conclude with a conclusion. First of all, what is a convolutional neural networks? A convolutional neural networks, as the name proposed, is formed by different convolution layers, activation layers, and also pooling layers. For the activation layer, usually it bound the extractor feature and usually use rectify linear unit redo, and the max pooling or the pooling layer usually downsampling, and another pooling, for example average pooling, will also be used. And with this set of convolution and activation set, then afterward you will usually end with a Fourier layers. One of the most common example, the AlexNet, is shown in the left bottom corner, and output shape is also clearly shown. And it's worth mentioning that for a general neural network itself, usually may use different kernel size, for example 3 times 3, 5 times 5. And of course the output channel length usually will be regular in, for example, 96, 256, and 384, etc. After we understand how CNN actually looks like and how the characteristic of a CNN, so for a constrained and platform, for example embedded system or smartphone, so how do we design the CNN accelerator, which usually have memory, limited memory, system latency and throughput is much more concerned, and the processor power usually is limited, and of course the hardware resources, for example how many DSP or maybe adders you have in the device. So how do we solve this problem? And we usually deal with the two major problems. First, usually is the memory usage and the compute intensity. For the memory usage, we usually will quantize the weights in order to reduce the memory usage by lowering the bit, for example low bit quantization, or binarize the weights into a binary representation. Afterward, for the computation intensity, we usually will prune the neural network. After our neural network is well trained, then we can remove some of the redundant neuron itself, so the kernel the kernel size will be reduced. And of course this pruning also introduces another form of problem we will discuss about. The challenges caused by the quantization, which we would like to introduce for the latest one, is incremental network quantization method, which it quantizes the weights into a 2 to the negative power value, and the quantization process is bit by bit. For example, a neural network is well trained, and then you quantize for a 50%, and then 50% of the weights will be converted into negative to the negative power, and afterward, and all the weights will be converted into to the negative power afterward. So how the IonQ, when the IonQ quantize the weights into to the negative power, so a cheaper shifter can be used. However, when the shifter is implemented based on a cheaper lookup table base, then it may lead to a heavy routing congestion, as it will require a lot of shifter itself. So this also need to be addressed a little bit. And the approximate computing can be used in order to ease the resources usage for the shifter itself, because we introduce a little bit, we simplify the shifter operation a little bit, so less lookup table use, and we will discuss later on how we design it. Afterward, we also need to understand what is the challenging of the neural network when it is pruned. So in general, there's different pruning method, and today we would just like to focus on the kernel level and filter level, which after pruning, the input and output channel no longer is a regular length. For example, for the AlexNet first convolution layer, before pruning is 96, so if you tie along the input output channel length, then you can use a 32, which does not require any zero planning. However, when the CNN is pruned for the AlexNet case, then the first convolution layer will be reduced to 40 the channel length. Then if you still planning as tiling along 32 fixed input-output channel length, then you will require a lot of serial pending, which you waste a lot of hardware resources, which is not contributing during computation. So actually we can do in a different tiling method, for example a 2D tiling which tie along the width and height dimension. However, this still introduces a problem. Although we reduce the input and output channel length tiling length, with the height and with 2D tiling, there's two edges of serial pending may caused by different kernel size as well. So in order to really solve this problem, we propose a 1D row-based tiling, which we only tie along the width, and then we fix the input channel length to 1. Then we can work along with the output channel tile as well. So we also duplicate the kernel in order to parallel compute the strike as well, so we do not waste any hardware resources and fully utilize the resources we have. And we will discuss a little bit more how the 1D row-based tiling actually works. Before that, we would like to emphasize our contribution. For our contribution, we propose a new tiling method which is named as 1D row-based tiling. And of course, in order to support this 1D row-based tiling with different kernel size, we also propose a configurable PU as well. So this configurable PU can have a better hardware flexibility and reusability as well. And as mentioned in the INQ waste containerization, shifter can be used. However, when there's a lot of shifter and the shifter is based on lookup table, then we need a trick to reduce the lookup table usage in order to ease a little bit of routing congestion in order to gain hardware performance. So a case study of 1D row-based tiling with a configurable PU and also the approximate shifter is done with the AlexNet based on INQ, and we implement onto a DE5 FPGA board. And of course, the DE5 support 2 DDR channel, and the controller is based on RTL design, and the configurable PU and all the activation and pooling layers is also implement onto the DE5. And during runtime, we need to configure the PU because we need to support different kernel size. And with the PU is configurable, then we also need a configurable PU buffer as well. So we will talk about it a little bit more in the next slide. Before that, first understand how 1D row-based tiling method actually is used, or how we implement the 1D row-based tiling method. The 1D row-based tiling method actually is that we, instead of working along the input and output channel, we work along the width dimension for the input feature, and also we can also work in the output feature width as well. Output feature width dimension as well. So we duplicate the same kernel to concurrently compute the strike, as convolution usually have a strike, usually 1, or maybe for the AlexNet first convolution layer is 4. And so we duplicate it in order to compute the entire row in once. And of course, when there's extra kernel which do not have enough space when the entire row is already flooded with a kernel, then we can also work along the output channel as well. Let's have an example so we can understand a little bit more. For the AlexNet first convolution layer, and the input image usually is 227, and the kernel size is 11, which the kernel width is also 11, and the strike is 4. So 227 minus 7 divided by 4 is 55, so we will require 55 set of kernel. So we can duplicate 55 set of kernel in a manner of a row base, then we compute the entire row in each clock cycle. So all the hardware resources can be used without wasting, and also we have a really high parallelism. Afterward, we understand a little bit more the 1D row-based tiling method. Let's first discuss our system building blocks in order to have a further understanding. The process element itself actually defined by the AlexNet kernel width and minimum kernel width size, which is 3. So as you can see in the diagram, there's 3 shifter, and we indicate the P as a one small cube in the left. And afterward, we can build along the PE and form a PU. And of course, with 4 PE itself, we can form a larger kernel size, for example, a 12 or a 2, 6. And then we can have support the kernel AlexNet kernel size of 5 and 11. However, there's still one serial pending, which is almost unable to avoid. So we can configure the PU in order to split or group in order to work with different kernel size. And afterward, when during computation, then we also need a configurable PU to temporarily store the results from the PU itself. And Afterward, when the entire result is ready, then we can shift it out instead of have individual set of redo and max pool hardware in the output tab of the PU buffer. Afterward, because we are working layer by layer, then we also need a layer buffer to temporarily store the entire layer, and then we can read it out afterward for the next layer, etc. Okay, let's have a better understanding by an example to understand how the PU grouping and splitting can be done. For the P itself, as mentioned, is defined. Free shifter is defined by the minimum AlexNet kernel size. Then with different kernel size, to support different kernel size, we configure PU based on the PE minimum size, which is 3. So we use 2 PE to form a 6. Then we can work with a kernel size of 5. And of course, these results can be selected by the output mux, which usually does not cost any much, because the complex logic board or the lookup table usually come with a dedicated mux itself, so we do not require additional hardware. And so this is much more cheaper to implement as well. And so during operation, the PU can dynamically group or split to support different input feature map width. So let's illustrate in the bottom left for the first convolution, AlexNet for first convolution layer, then 55 set of kernel is required. Then all the PU is joined together in order to work the entire row. And after the first convolution layer, for the second convolution layer, the input feature map is reduced to 27. Then we can chop it into 4 set in order to work along the output channel as well. Then after we understand how the PU can be configured and grouped and split in a different manner, we also need to understand how we can reduce the PE resources a little bit, as there's a lot of shifter to work with. For the INQ weights, as we understand, is a shifting base, so the weight is quantized into a shifting manner. So the data is represented in a 5-bit, 1 sign bit, and 4 shifting bit. And then we require a barrier shifter with arithmetic shifter, is because the feature can either be positive or negative, and the weights also can be positive or negative. Then we need a really complex or an arithmetic shifter, which also require more lookup table hardware usage. Usually the sign extension is also needed because it's an arithmetic shifter. And so first you need to have a arithmetic shifter, then usually you also need adder chain in order to support the sign extension and the value positive to negative conversion. And so the lookup table need to place really close in order to gain maximum hardware performance. And however, when the shifter is getting more and more and the neural network is getting denser and denser, then this routing will be much more harder, and the routing congestion will really matter a lot. So the overall system performance will degrade a lot. So how do we solve this problem is that we can simplify the shifted hardware design by maybe approximate computing. So how we work is that we, instead of implement the arithmetic shifter, we try to use logical shifter, which do not require a sign extension, and we do not need adder chain to place really close to each other. How this actually works is that the feature map is we check the feature map either is positive or negative, and then we all convert into a positive value, and then we just logical shift it to the right based on the shifting bit, and then afterward we flip it. Depends on the sign bit of the feature map and the weight itself. So we have introduced a minimum error, however still able to save a lot of lookup table usage. Per shifter, almost 30% of lookup table is saved. Afterward, we need to also experiment a little bit how approximate shifter the INQ algorithm and also the 1D row-based tiling performance. First, let's look at the experiment results. For the AlexNet and INQ without the normalization layer, usually degrade. We investigate and the performance is degrade around 1%. And afterward, the AlexNet with approximate shifter with no normalization and INQ achieve a similar network accuracy as a normal shifter, which means that our approximate shifter gain hardware performance and still do not degrade many new network accuracy. So this is really a good result. And of course, our system able to achieve a 214 gigabits per second. So we achieve a really good throughput compared to the previous work is around 1.8 times better. and the latency is almost 20% lower than the previous work. So this is a good result. And however, without the BIOS itself, for the RxNet usually suffer 2%, and the accuracy loss, but still able to gain overall system performance of about 6.5, and the latency drop around 0.6 milliseconds, which is really much. And last, we also measure a little bit our D5 board power consumption. Without anything, the D5 idling power is around 30 watt. Then we program it, usually go up to 20 watt, and when influenced, then it's around 22 watts. So overall, the system only use around 22 watt compared to a conventional graphic processing unit almost require 100 watt power consumption. Then this is much better than with a resource constrained platform. Then we can implement easily onto, for example, advanced system or smartphone. Last but not least, I have a conclusion is that in this work we try to propose a new tiny method to settle the prune the neural network, and afterward we also introduce a configurable PU designed to support different kernel size and gain parallelism during computation. And we also try to solve the INQ shifter lookup table, cheaper lookup table based shifter designed by approximate computing, and so less lookup table can be are used, and which means the routing congestion is a little bit more. Of course, we're also able to achieve a better system performance compared to the latest optimized RTL work on the same FPGA board. However, there's always a limitation in this work, is that we remove the normalization layer, and the normalization algorithm itself for a lookup table shifter base is really hard to reuse. However, it's worth mentioning that in our shifter based CNN accelerator design, it can also convert into a DSP base. However, we want to understand a little bit more the resource constraint scenario implementation, how the hardware will perform, and how the lookup table will consume, and the shifter will cause any kind of problem. So we try to settle all these problems in this work. And thank you for your listening, and hope you all understand what we are trying to demonstrate. And if you have any questions, please feel free to ask, and thank you for your time.